Okay. And if it would release more energy, then you create another problem, because then it has the tension to expand if it would release more energy. Because, okay, it's a gas, plasma thing. Yeah. Okay, and we're going to look at the properties, the physical properties of a gas, a plasma. Now we know that based on gases, the gases, they have several properties. One of them is the ideal gas law. Yeah, we know that. But the ideal gas law is only applicable to gases under mild conditions. Yeah, on the atmospheric or lower pressure conditions. We know that the sun is most probably not ideal. The temperature is 15 million degrees hot, whether you express it in Kelvin or in Celsius degrees, it doesn't matter in this case. So it's 15 millions high. Yeah, we can only achieve that here in tokamaks, the donut-shaped fusion reactors, which lift the temperatures up to 100 million degrees. So fusion, but the amount of particles is very low. So it's actually a vacuum at 100 million degrees. So, but that's the only situation where we can get those temperatures. But in most cases, gases do not behave ideally. So, in the case of the sun, where the pressure and the pressure and the temperature are sky high, you know, there are pressures about 2 to the power of 18 Pascal. Yeah, that's high. We cannot achieve that here on Earth. Yeah? So those situations imply that the gases and the plasma is not ideally behaving. Yeah. Okay. Well, here on Earth we have trouble in predicting and to forecast about non-ideal gases. There are some equations. This is one of them. This is the Redlich-Kwong equation. Yeah, and even that is not ideal or not perfect to the real situation. If you would compare the graphs, then it's not. This is just an approach, and even the approach does not function perfectly. Yeah. Okay. So but suppose that the sun is an ideal gas. Yeah. And we take this one for as a fundament. Yeah. Which most probably we cannot. But okay. But it shows us something. Yeah. The number of particles has to reduce. Yeah, the sun is burning by fusion. Yeah, fusion is decreasing the number of particles. We discussed it a moment ago. Yeah, so the number of n is decreasing. That's one thing. The number of particles is also decreasing because the sun evaporates, so to say, or how do you say, emanates particles, yeah, solar winds and so on, and protuberance flames, yeah, millions of kilometers high and hundreds of thousands of kilometers high. So those particles are sent out, yeah. So the number of n is decreasing. We know that. Gravity is keeping the whole thing together, luckily, yeah. But that means that the pressure has got to be stable, because if the pressure would not be stable, it was expanding. If the pressure would reduce, then it will shrink. Yeah. So, and also the temperature has got to be the same whether you speak in billions of years ago or 6,000 years ago, as the Bible says. But if you say the temperature must be must be the same according to evolution thinking wise. Yeah. Otherwise, evolution has a problem anyhow. But it has anyhow. But I'm going to show you in a moment. So, if the number of particles is decreasing and the pressure and the temperature is remaining the same, yeah, then the volume must increase if the number of particles was bigger. Yeah. So the volume was increased. The sun was bigger. Yeah? And then we have a problem. If you think billion of years ago wise, evolution wise, because if the sun is bigger, no water can be here on Earth. So evolution could not have taken place. Yeah? And the sun must be shrinking because of what I mentioned a moment ago. Less particles first. The energy content, the energy release is getting down because of the fusion. Yeah? Increasing number implies less energy is coming released, so less particles and less energy released spread out over less particles, so the sun has got to shrink. Yeah? So a couple of arguments why the sun has to shrink. It cannot stay bigger. Well, in that case, you run into a problem if you think billions of years wise. One way or the other way, in Dutch we say to the left way around or to the right way around, you end up with a problem if you think in billions of years terms. Yeah, the sun, however you reason, the sun must have been bigger. Yeah? If you calculate that back on billion scale, billion years scale wise, then the sun must have been that big, yeah, that we on Earth, the temperature was such a high temperature that water could not exist here. Life could not evolve here. There is only one solution, one way or the other way, yeah, that the sun is not as old as evolutionist people try to say. Yeah? And what the Bible says, that the sun is 6,000 years old, is more assumable. Yeah? Also based on this type of reasoning. Yeah? That the sun has to decrease. And that's actually what is measured. It's not taken seriously, I know, but it cannot be different based on the fusion reactions. Yeah? So, a shrink has got to take place because less particles, yeah, going to higher atom numbers by fusion. Yeah? So the less energy release per reaction, yeah, especially in the beginning, because the graph is the steepest. Yeah? So the energy release is getting slow, is decreasing quicker. Yeah? Irradiate energy, the sun, I mean that's why we're living here. Yeah? Okay, hi, hello. And if there would be more energy release, then it would imply that the sun had to be bigger anyhow. Yeah, because more energy means hotter. Yeah, so that it would be expanded more. So to the left or to the right, you run into a problem that the sun would be bigger, and so less water could be here, and so no evolution could have taken place. If you think billions of years wise. Conclusion, there is only one solution. Yeah, it's not billions of years wise. It's only 6,000 years that the Earth is old. Yeah. So, and then you come in biblical proportions. Yeah. So the Bible is right, also in this perspective. Okay, that's where I want to leave it up here. Okay, thanks for your attention.